In pursuit of sharing technical knowledge and just to gear up the new generation of engineers, myself Pranab is here to deliver today's presentation, Power Transformer Part 40. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with performance limitations of conventional tap changers. Depending on the working mechanism as of the load current switching performance, OLTCs are categorically divided into two types. One, diverter switch type OLTC, that is in figure 140. Another is selector switch type OLTC, as of figure 139. Diverter switch type OLTC, one which consists of a tap selector and a diverter switch. Number two, a tap selector pre-selects the tap winding without switching any current. Number three, then the diverter switch transfers the load current from selected to the pre-selected tap during the switching operation. Selector type OLTC, which has the combination of functional activities of tap selector and diverter switch. Number two, it selects a tap winding during transferring the load current. See the diagram, that is elements of the selector switch type OLTC. See the oil valve, conservator, conservator connecting flange, bevel gear, top cover, cylinder, fixed contacts, moving contacts, fixed contacts and moving contacts of the selector switch. Previous one is the changeover selector, bottom valve drain screw, current collector terminals, transition resistors, shielding rings, position indicators, air release valves, pressure relay. And the diverter type OLTC, there is diverter switch in the upper hub and the tap selector in the lower hub, and fiber glass compartment is there. Main components of diverter switch: one, fixed and moving main contacts, fixed and moving transition contacts. Number three, transition resistors, spring action mechanism, tap position indicator, and worm gear assembly. Now see the points. A perfect oil type structure is thus to be configured between the diverter switch and main transformer tank so as to prevent mixing of oil outside the switch chamber with the oil inside, which would have been contaminated due to the switching operations. Concept for the implementation of vacuum switching technology. During changeover selector operation, there must have some breaking capacitive currents followed by recovery voltages, and for which there would have been an obvious cause of switching sparks and low energy arc. As the OLTC unit is completely immersed in oil, so free gases that to be produced due to these switching sparks are thus to be fully dissolved in the oil. Such happenings may have to influence the resultant process of the transformer oil dissolved gas analysis, and the suspected presence of acetylene in the transformer oil would have always been a serious issue. Therefore, the switching capacity itself is quite pertinent with the function of the contact design, contact speed, and arc quenching agent. An OLTC commonly preferred to mount in the high voltage side of the power transformer as because of lower load current to handle. Switching arc, as it has been reduced, so the contact lifetime would obviously be enhanced because it has to handle lower load current. Such consequences would also have to slow down the formation of carbon while oil is used as an insulating medium. In spite of developments in the structure of the conventional type of on-load mechanical tap changers, where oil being the arc quenching agent, but such occurrence of small switching arc is still be one of the most considerable drawbacks and limitations in their capabilities of features and features. In order to circumvent these limitations and drawbacks, vacuum switching technology, figure 141 for on-load tap changers have been recommended, where vacuum being the arc quenching agent. Reactor type OLTC with one vacuum interrupter per phase. But in case of resistor type OLTC, two vacuum interrupters are required per phase. Vacuum switching technology is mostly preferred to use in the diverter switch type OLTC. By the newly introduced compression springs in spring mechanism of conventional resistor type OLTC that has made to tend the total time span of transition resistor in circuit during a tap change process significantly limited to a few periods. As of the compactness of modern conventional resistor type tap changer, with being lack of wear of diverter switch contacts because of high speed braking system, and also because of the circulating current at unity power factor, the contacts have a lifetime of 2,50,000 operations as compared to the 10,000 to 20,000 operations for reactor type tap changers. To provide maximum reliability, further implementation of vacuum technology that has to improve contact breaking capacity, which leads to increase the contact life and to reduce maintenance criteria. See the diagram. Resistor vacuum type OLTC for in-tank installations and in oil-filled power transformers. Number B is the vacuum switching technology implemented in the diverter switch type of OLTC. The high-speed resistor vacuum type OLTC for in-tank installations for oil-filled power transformers is shown in figure 142. The purpose of operation has to depend on in which direction the center shaft is rotating. There are two different contact sequences as of figure 143 are obtained. Either the main contacts operate first or in the other direction, the transition contacts operate first. By using auxiliary contacts in combination with vacuum interrupters, where the contacts are used for carrying current and the vacuum interrupters are being deployed at the time of energized switching, two vacuum interrupters are thus to be required per phase for obtaining two different contact sequences as mentioned. See the switching sequence moving with resistor side. Left side is the main side and right side is the resistor side. Auxiliary contacts in combination with vacuum interrupters. Number A, position for continuous load through fixed tap contact 1. Number B, resistor auxiliary contact leaves the fixed contact 1. That is, resistor side is shifted and in towards the tap number 2. C, resistor vacuum interrupter opens. Number D, resistor auxiliary contact enters fixed contact at tap 2. E, resistor vacuum interrupter closes, causing a circulating current. Number F, main vacuum interrupter opens, breaking the circulating current and commuting the load current to the resistor branch. G, main auxiliary contact leaves fixed contact 1. H, main auxiliary contact enters fixed contact 2. Last one, main vacuum interrupter closes, commuting the load current to the main branch. Continuous load on fixed contact 2. Now, see the points. Number 1, contact sequence. While the transition contact operates first, together with the physical position of the vacuum interrupter is shown in figures A to I. Number 2, in the other direction, that is in the opposite direction, while the main contacts operates first, that is from tap 2 to tap 1, then the contact sequence will follow the sequence just opposite to the previous diagram, that is shown in figure A to I. The use of vacuum interrupter that complying with high-speed resistor type OLTC for in-tank installations at oil-filled power transformers has been successfully implemented since 1960s. The total unit is mounted inside the transformer tank and rather suspended from the transformer cover. Resistor type OLTCs equipped with arc quenching in vacuum interrupters are suitably used for transformers up to 2300 MVA rating with BIL rating of 1175 kV and a current rating of 1600 ampere when placed in the neutral point of the winding, as shown in figure 143A. Having with compartment type design, the application of vacuum interrupters in reactor type OLTCs would have been made to introduce in the United States of America since 1980s. Two possible OLTC setup of power transformers. A three-phase start point connection where one OLTC is needed for all three phases. Transformer neutral point is in the tap changer. B three-phase delta fully insulated connection with three OLTCs, three numbers of OLTC. Now, see the diagram, the essential components of vacuum interrupters. Moving contact, stem, bellow shield, ceramic cell, fixed conductor, flange, movable end cover, metal bellow, moving contact, fixed contact, arc shield. The essential component of a vacuum interrupter is shown in the figure 145. Vacuum interrupter is mainly configured with a vacuum sealed ceramic bottle with stainless steel bellows to allow electrical contact movement in opening and closing operations. Tap changing device equipped with vacuum interrupters can be designed on the basis of contact erosion behavior, current breaking capacity, contact resistance, and the value of chopping current characteristics. The contacts are made of a variety of materials depending on the application and design criteria of vacuum interrupter for its long contact life, rapid recovery of voltage withstand rating, and control of over voltage due to current chopping characteristics. Again, I repeat, the contacts are made of variety of materials depending on the application and design criteria of vacuum interrupter for its long contact life, rapid recovery voltage with withstanding rating, and control of over voltage due to current chopping characteristics. Vacuum interrupter technology, some distinct advantages. As of conventional diverter switch tap changers, it has been exhibited that there are an exceptional wear of contact surfaces due to arcing, and the resultant occurrence of byproducts from the oil as used would have to cause pollution in the form of particles. Extremely tiny constituents of particles will be in suspended form, while the larger one will be accumulated as sludge at the diverter housing bottom. To assess actual conditions of diverter switch contacts, an overall is being scheduled in every 7 years, which includes cleaning mechanism, checking for contact wear, oil filtration, and checking its dielectric strength. Vacuum switching technology that has proved its technical superiority over conventional diverter switch tap changers. Vacuum interrupter is the core component of vacuum switching technology, where separation of the electrical contacts with having metal vapor arc, which is quickly extinguished in vacuum bottle. When the contacts are separated in vacuum interrupter, then the current as interrupted that has to initiate a metal vapor arc discharge which flows through the plasma until the next current zero. The arc is thus to be extinguished quickly at zero current, and the conductive metal vapor that has to condense on the metal surfaces within a matter of microseconds. As of high rate recondensation of metal vapor on contacts that has made to extend the contact life. Ability of vacuum interrupter depends largely on the material and form the contacts where most acceptable material composition as established is an oxygen-free copper chromium alloy. Contacts as being configured with this sort of material composition has the properties to exhibit good arc extinguishing characteristic with having a significantly less tendency to contact welding, less tendency to contact welding, and always intends to low chopping current while switching inductive current. As of the higher contact forces, the contact resistance is constantly below, that is, in the order of micro-ohm range. High vacuum always possesses extremely high dielectric strength. However, the post-arc phase would have the most significant role in current interruption process, since during that phase, the dielectric strength of vacuum has to be recovered. While the current across the contacts tends to zero, a high frequency transient voltage that appears across the contacts. Under the influence of this voltage, the arc tries to restrike, and hence it is denoted as the restriking voltage. Rate of rise of restriking voltage can be defined as the ratio of peak value of restriking voltage to time taken to reach to the peak value. It is called rate of rise of restriking voltage. At zero current, the arc would have been extinguished only when the rate of rise of restriking voltage between the contacts is less than the rate at which the recovery of dielectric strength of the medium vacuum between the contacts regains. It has been exhibited that the dielectric recovery strength of vacuum can be enhanced by increasing the separation of contacts and decreasing the arc time. Such type of complexity has to be characterized more sensitively at the time of design. The philosophy as indicated that the dielectric strength of the contacts can have to recover at a very fast speed, as because of the metal vapor which is localized between the contacts would have to diffuse rapidly, due to complete absence of gas molecules. Vacuum has a very fast recovery strength which is in the range of more than 10 kV per microseconds. Because of this commendable technical feature, vacuum can therefore be easily withstand all sorts of high transient recovery voltage and rate of rise of restacking voltage. Let's stop here. Further to be continued at later stage. Thank you. Thank you for patient hearing and seeing the video. Kindly do like, share, and subscribe. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section, please. Thank you.